So, first off, we have a guest today. See the doggy in the background, he's hanging out. This video is for somebody requested this in the discussion board, and that is deriving the forward difference, backward difference, and central divided difference equations from a Taylor series. Taylor series approximations. Because what the forward difference, backward difference, and central divided difference methods are doing are approximating the first derivative of a function. And that first derivative appears inside of the Taylor series. So if we rearrange the Taylor series a little bit, we can actually derive the equations for those guys. So let's go ahead and we'll start with forward. And if we don't do the Taylor series technique, in general, what we see is that if I have 2 points, and I want to find the derivative here at x, and I have some point that's h away, this is going to be x plus h. So for example, if x was 3 and the second point was 7, that means that h is 4 because that's the distance between the points. And what we do is find the slope between those points. And that's how we approximate our derivative. So our slope, which is our derivative at the point x, that will be y2 minus y1, which will be the function value at x plus h, minus the function value at just x, divided by x2 minus x1, which is x plus h minus x. So we get our forward difference approximation as f of x plus h minus f of x divided by h. That's our forward difference approximation. Just by computing slopes. We didn't do anything with Taylor series, but that's the general idea behind it. So if we were to go to a Taylor series approximation, and the Taylor series says that if I want to compute a function value at some distance h away from a known function value x, I can look at all of the derivatives of x multiplied by some power of h, like that. So what we want to do is we want to solve for this guy, because that is our derivative. And let's solve for that exactly, bringing everything over to the other side. So we're going to bring this over. We're going to bring all this stuff over to the left-hand side of the equal sign. So that'd be f of x plus h. That's still there. Then we'll subtract f of x. We will subtract the second derivative. Subtract all the other derivatives. And that is exactly equal to f prime of x times h. I haven't divided by h yet. If we divide by h, we end up getting f of x plus h minus f of x. I can divide both those terms by h, or if I want, because it's a common denominator, I can just have them all above the h, at least the first two terms, minus our second derivative, h over 2 factorial, minus dot, dot, dot. That is equal to the exact value of my first derivative. So this whole thing, this is the true value. That's the whole thing. And just this guy is the approximate value, because that's what we're doing our forward divided difference for. So if we were to find our true error, it would be that whole thing. I'll write in red. Minus and then we'll subtract our approximate value, which is just the forward divided difference method. And what we see is that this term and this term go away, and we end up with our true error being equal to our second derivative minus higher order terms. And what we do is that if we say that h is very small, if h is very tiny, we'll neglect our higher order terms, basically meaning that everything out here is too small. We'll just say it's approximately 0. So that tells us that our truncation error is on the order of h because of the fact that it's proportional to h. In regard to actually deriving the forward divided difference equation, we would say up here that if h is small, we'll just neglect this, and then we're left with our divided difference method, which is what's on the left, and that's underlined in blue. So that's how we do forward. Let's do backwards. If we do backwards now, what that means is that we have a point x, and now we're going to reference that to some point behind it at x minus h. So if we do our derivative, this will be y2 minus y1. Maybe I'll say that this is my second point, my y2, my x2. And this is my first point. And it doesn't matter which one you choose to be first or second. It'll work out the same, the math. One of them will just have an extra negative sign that ends up going away. But let's say that the x1 is my second point. So that'd be y2, which is f of x, minus y1, which is f of x minus h, divided by x minus h, right? This is x2 here, minus x1, x2 minus x1. So this ends up being f of x minus f of x minus h over, and if we look inside of this denominator, we have x minus x, the x's go away, and then you have a negative h, that leaves us with a positive h, and this is our backwards approximation. Nothing crazy. If we do a Taylor series now, what I want to do is instead of having some point at x plus h, I will have x minus h. So now I'm trying to find the exact function value at a point some distance to the left of our known point. So we'll say that this is f of x plus f prime of x times the distance between the points, which is minus h, plus f double prime of x times minus h squared over 2 factorial plus dot, 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 just like we did before. So this will be f of x. That minus h will end up coming to the front, so we'll have minus f prime of x times h, and then that negative h squared is still positive because we're squaring the negative number, so that would be f double prime of x, h squared over 2 factorial. The next term would actually be negative. We kept going because it would be negative h cubed, so that negative would pop out in the front, which is fine. We're going to end up neglecting it anyway, because we'll assume that h is tiny and those terms will be negligible. So again, we do some algebra. We bring over everything to the left. So f of x minus h, we'll subtract the f of x. That's this term. We will subtract this guy. So minus f double prime of x, h squared over 2 factorial. And then, everything else here, we will eventually cancel out. That will be the exact value of negative, let me make sure that's clear, negative f prime of x times h. So now if we divide by negative h, we will get f of x minus h minus f of x divided by negative h. This guy divided by negative h will cause the negative signs to go away. So we have plus f double prime of x times h over 2 factorial. And then we have all those other terms, and that will be our exact value of our first derivative. And we can fix this here with that negative h if we switch the subtraction in the numerator. So this would be f of x minus f of x minus h over h plus double prime of x. I'm just rewriting this part now. That is our exact value of our derivative. So this whole thing here is our true value. And then this, of course, is what we had before for our backwards divided difference approximation. So what you see is that if you were to subtract the true value and the approximate value, that we end up with this thing here. This is our truncation error. This is also on the order of h. And that's assuming, of course, that we neglect the higher order terms, which is reasonable as h gets very small. So our truncation error is proportional to h. And we saw the same thing for our forward divided difference method. They are essentially equivalent in regards to our error. One of them will provide a value slightly greater than the actual derivative. One of them will provide a value slightly less. So the last case is our central. And our central divided difference method says that we have 3 points that we're looking at. And what's important is that all the points are spaced evenly apart. So this distance here is h, this distance here is h. So if I have, a bunch of points or whatever, let's not do it there, let's do it here. What we'll do is compute the slope between the point that's ahead and the point that's behind, meaning that our point of interest is actually in the center between the 2 points that we're finding the derivative between. So really, we're trying to find the derivative between those 2 points. So say that f prime of x, if we say that it's y2 minus y1 over x2 minus x1, and we'll say again that this is our second point, and this is our first point, our y2 is f of x plus h, minus our y1 with f of x minus h, divided by the distance between the points, which is x plus h minus x minus h. That's x2 minus x1. x2 minus x1. So again, this will be f of x plus h minus f of x minus h, divided by, if you do that algebra in the denominator, you see that the h's will double and the x's will cancel. X's cancel because it's x minus x. The h will be h minus negative h, which gives us 2h. And that makes sense because the distance between those 2 points is 2h. We can see that right here. H and h is the distance between the 2 points. So this is our central divided difference method. That's our central divided difference first derivative approximation. Okay. Cool. So let's do our Taylor series again. What we need for the Taylor series, though, if we actually look at this equation, let's go back to this equation. We see that we have an f of x plus h and an f of x minus h in our equation for our derivative. So that should give us kind of a hint that we need to do a Taylor series expansion for both f of x plus h and f of x minus h in order to combine the equations and end up with this approximate form. So let's do that. Let's say that we have our f of x plus h. This will be f of x plus f prime of x times h plus f double prime of x times h squared over 2 factorial plus dot dot dot. And if we do f of x minus h, we'll get f of x minus f prime of x times h. Again, this is the same thing we just did with backwards, where that h is actually negative h, and that negative comes to the front. And then this term ends up being positive because we're squaring that negative term. And what we can do is we want to make sure that we retain, we want this term, we want this. So if we do the top equation minus the bottom, that will cause our f prime of x term to remain and everything else actually goes away. At least the terms that we see on the screen will go away. So let's subtract top minus bottom. To be f of x plus h minus f of x minus h. That's going to be equal to, that was the left side of the equal sign. If we look at the terms on the right side now, if we subtract those guys, they are the same sign, that goes to 0. If we subtract f prime of x h from f prime of x h, well, there's an extra negative in there, we end up getting 2 f prime of x h. And again, this is positive minus a negative, so we double. This term will end up canceling. But let's take into account that extra term that we didn't write here. That will actually be the term that's written next here. What is that, do you think? Maybe take a sec to pause and figure out what that is. I'll assume that you pause now. But that'll end up being plus 2f triple prime of x times h cubed over 3 factorial, plus dot, dot, dot. Now what I want to do is isolate my derivative, this guy. So I'll bring everything on the right over to the left. So I get f of x plus h minus f of x minus h minus 2f triple prime of x times h cubed over 3 factorial minus dot, dot, dot. That is equal to 2f prime of x times h. This is still the true value. We haven't done any neglecting yet. So if we divide by 2h, we'll get f of x plus h minus f of x minus h divided by 2h, this 2 and that h. Right? We divide by those to isolate our first derivative. Minus, well, we divided by the 2's, those go away. We have f triple prime of x, yet h cubed divided by h is h squared. Make sure it's better too. Divided by 3 factorial minus a bunch of other terms, and that is our derivative. And just like we did before, what we see is that this whole thing is our true value. And then this guy here is our approximate value. And to find our true error, we'll subtract our approximation value from our true value. And we'll see that this here, a different color, this guy here, that is our true error. And if we neglect all the other higher order terms, which will be something like h to the 4th, h to the 6th, etc., we'll see that our error is on the order of h squared. And again, the benefit of that is that if I were to decrease h to improve my derivative, I will end up decreasing the error by an extra factor of that. So if I were to half the distance between points, I would quarter the error. If I were to third the distance between points, I would ninth the error because we're squaring the distance. That's what ends up happening as we decrease our value of h. So I hope that that makes sense. If it doesn't, let me know, and we can chat more this week before your exam. Okay, thanks. Bye.